Earlier this year, I got a call from an old friend. He asked if I'd heard of the Space Development Agency. The infant agency was moving fast, and like most of us here, I'd been following their progress. I said to him, "Yes, why do you ask?" "I'm part of the transport cell," he said. "We're working to build a mesh network and need an optics guy. Know anybody?" I thought, hey, I'm an optics guy. I said, "Yeah, maybe, tell me more." He went on to tell me about the plans for the transport layer. SDA's goals were ambitious. They wanted to implement a high bandwidth, low latency mesh network. They wanted to pass bulk IBS data, and they wanted to connect to Link 16 networks on the ground. And for me, the most exciting part, the intersatellite links would be free space optical comm systems. They wanted to field all this, plus a tracking constellation, and they were planning to launch in 2022. SDA was working to procure Tranche 0, the first in their spiral development plan. T0 would field 30 to 40 spacecraft, including around 100 optical intersatellite link terminals. They hoped to let contracts to multiple spacecraft vendors with multiple optical comm vendors. The challenge for the optics guy? Ensure that the optical comm terminals from different vendors could talk to each other. This would mean shepherding the teams through the challenge of setting the specs that would allow the T0 performers to communicate and, moreover, to allow comm terminals used by other organizations in both government and industry to join the network. Needless to say, I took the job. Since then, SDA has let 4 Tranche 0 contracts, 2 for the transport layer and 2 for the tracking layer. Today I'm going to tell you about SDA's mission and vision. I'm going to describe the architecture and the spiral development process. And I'm going to talk about the recent awards. And last but not least, since this is the Optical Communications Workshop, I'm going to tell you about the SDA OISL demos, the OISL standard, and I'm going to tell you how you can participate in development of that standard through the OISL community of interest. Now let's talk about a shift in the way the Department of Defense does business. Previous national defense strategies would talk about the great power competitions and how we needed new and better technology. In 2018, that strategy shifted. It said that we had the best technology, but we're just horrendous at getting it to the field rapidly. This observation formed a cornerstone of the 2018 National Defense Strategy. Getting new technology to the warfighter rapidly is one of its objectives. In order to ensure that we modernize in a very efficient and rapid manner, the department established the Undersecretary of Defense for Research and Engineering. The office's goal? Modernize the department's ability to conduct warfare. To do this, USD R&E had several different thrust areas, one of which is space. Space Development Agency fits in here because we are developing the next generation national space defense architecture that we think will disrupt the way the department currently does business. The DoD Space Vision followed the 2018 National Defense Strategy. To quote from this vision, DoD will usher in a new age of space technology and field new multi-domain systems in order to deter and, if necessary, degrade, deny, disrupt, destroy, and manipulate adversary capabilities to protect U.S. interests, assets, and way of life. This new age will unlock growth in the U.S. industrial base, expand the commercial space economy, and strengthen our cooperation with allies and partners. To accomplish these goals, the department will harness a blend of commercial and government technology, rapid prototyping, experimentation, collaboration with key allies and partners, and enhanced government-commercial relationships. It goes on to say that there are 8 capabilities that the department wants. These are codified in SDA's 8 mission areas. If you look at the slide, you can see them represented around the globe. Let's go through them. Targeting support. We need persistent global surveillance for advanced missile targeting. Tracking. Indications, warning, targeting, and tracking for defense against advanced missile threats. AP&T. Alternative position, navigation, and timing for GPS-denied environments. SSA. Global and near real-time space situational awareness. Emerging capabilities. Development of deterrent capability. Common ground and support. Responsive, resilient, common ground-based space support infrastructure such as ground stations and launch capabilities. Battle management. Cross-domain, networked, node-independent battle management command, control, and communications, BMC3, including nuclear command, control, and communications, NC3. And finally, global surveillance. Highly scaled, low latency, persistent, artificial intelligence-enabled global surveillance. Focus these down, and what we wanted to do is start and end with the warfighter. U.S. Space Command and U.S. Space Force talk about what is needed to fight and win in space. They also talk about space control and those kinds of activities. These are obviously incredibly important. Space Development Agency is tackling a different set of missions. We're asking several questions. What does the actual battle that will happen on terra firma look like? What is needed to be able to make sure that we can win on the ground? And to enable the win, what capabilities do we need to provide in space? There are basically two capabilities that we plan on delivering initially, and this is what we're focused on for the first set of missions. Number one is beyond line of sight targeting for time-sensitive ground and maritime targets. What that means is that we want to be able to detect, track, identify, form fire control solutions, and send those data directly to a weapons platform. We want to be able to do all of that from space without the need to go to the ground. That is SDA capability number one. Number two is to do the exact same mission, except instead of doing it for time-sensitive ground and maritime targets, we want to be able to do it for advanced missiles such as hypersonic glide vehicles, dim upper stage cruise missiles, and the like. How will we make all this happen? We've divided the SDA constellation into layers. I've mentioned the transport and tracking layers already, and here we add the nav, custody, and deterrence layers to the list in order to fulfill those 8 capabilities from the DoD Space Vision. These layers will comprise the SDA constellation, and the spacecraft will be connected throughout by optical intersatellite links. The constellation will also have the ability to send data directly to weapon systems on the ground via existing tactical data links. Link 16 is the first of these links, and as I mentioned, it will be demonstrated on the Tranche 0 transport layer. In the future, we'll also be able to send those data down to the battalion level commanders through systems such as the Army's Titan ground system. Optical or KA links to the ground would then allow data to be disseminated in theater. The transport layer is the backbone of how all this ties together. Next, we have the nav layer. Essentially, we get that for free. How? We'll have an optically connected mesh network of satellites. The OISLs do a really good job of transferring time. This time transfer capability will serve as the core of the alternative PNT system. The nav cell will demonstrate this APNT mission in Tranche 0 and will be able to transfer PNT information to Link 16 subscribers on the ground. Next, let's talk about those two capabilities SDA will demonstrate. These require the sensing layers, which will consist of the custody and tracking layers. Custody is our ISR network. This will be a constellation of satellites. We're relying on mission partners to build these, and they'll provide optical RF, ELINT, and SAR capabilities that will enable detection, tracking, and firing solution generation against those ground and maritime targets. Next, we have that tracking layer that I've already discussed a bit, which will consist of OPIR systems for tracking missiles. These will allow us to do detection, tracking, and fire control data formation in that domain. Both the custody and tracking data are sent and fused together through computational capabilities provided by the transport network. The firing solutions can then be sent to weapon systems in order to engage targets. I'd like to mention the government-industry partnership here. I mentioned that the custody satellites will be primarily mission partner satellites. These could be either government or commercial partners. One of the OISL interoperability objectives is to make sure those partners can connect to our transport network and be able to help form a fire control solution. The third sensing layer that I didn't mention yet is the deterrence layer. Right now we're just in the study phase. That's our space situational awareness layer. Its targets are in geosynchronous through cislunar space, and the products will flow rapidly to customers such as the NSDC. Finally, we have the battle management layer, which spans across all other layers. Battle management is really the magic that makes all this happen. The more you pull the thread on what we've said here, the more you realize that what we describe is an extremely difficult problem that sounds very magical. We're going to be able to tip and cue multiple sensors and be able to move those resulting data products across an ad hoc network and be able to actually form and fuse fire control solutions that get to weapons platforms. Again, a lot of magic has to happen here. That's the job of the battle management layer. This layer is, in essence, a computational cloud in space that resides mostly on the transport layer spacecraft. This is where we will actually keep the smarts to be able to fuse data utilizing advanced algorithms on board the spacecraft, and be able to tip and cue autonomously, and then again autonomously route fire control solutions to weapons platforms. SDA has a lot on its calendar. There are several experiments and prototypes both at SDA and with mission partners that will inform Tranche 0 and Tranche 1. We are working the Tranche 0 architecture demonstration, and we're planning for the Tranche 1 demonstration of regional persistence. SDA is closely following DARPA's Blackjack demonstration program. This effort has informed a lot of our P-LEO strategy and is a key demonstration of optical crosslinks on small spacecraft. SDA has partnered with MDA on an overhead persistent infrared demo slated for launch in 2021. 2 sets of OPIR tracking spacecraft are being developed, one of which is a medium field of view demonstration that's going to launch in early 2021, and then another is a wide field of view system that's going to launch in late 2021. The transport cell has 2 demos that will demonstrate OISL technology. The first will launch in late 2020. We're teamed with AFRL and DARPA to make this demo a success. The second optical crosslink demo from another vendor is scheduled to launch in mid-2021. These transport experiments have a goal of demonstrating both space-to-space optical intersatellite links and space-to-ground free space optical comm downlinks. These efforts will put SDA well on the way toward establishment of a vendor base that can provide those all-important interoperable OISLs. MDA and SMC are working on ground systems. These include the Casino Processing, Exploitation, and Dissemination Prototype, the Casino Mission Data Processor, and the HBTSS ground system. I've already mentioned the Tranche 0 constellation, which will consist of 20 transport layer space vehicles and 8 wide field of view tracking layer space vehicles. These are scheduled for launch in late 2022. Those first Tranche 0 systems will be followed by the launch of 2 medium field of view hypersonic and ballistic missile tracking sensors, again HBTSS, space vehicles, and those are being launched by MDA. Finally, we have the Tranche 1 effort, which will bring SDA to the point of initial capability. This effort will provide regional persistence through launch of 200 transport space vehicles and 40 tracking space vehicles. Transport Tranche 1 is shown on the schedule in blue, which represents that it's funded, whereas tracking Tranche 1 is shown in gray, which represents that it is not yet funded. This gets us through early 2025, and in total, by then we anticipate launch with mission partners of over 280 spacecraft. SDA is going to be busy. Looking into the future, Tranche 2 is when we will achieve FOC. This is when we hope to have full global persistence through fielding hundreds more satellites, giving us full global coverage. Tranche 3 is when we start to fold all of the lessons learned from the earlier tranches back into the system, as well as transition new technology that's currently being developed, such as through the FNC Cubed program. Through additional tranches, we'll field new space technology every 2 years. Through this spiral development approach, we'll set a cadence such that we don't slip timelines. Rather, we intend to add technologies as they become available. SDA has had a lot going on recently. Let's take a minute to talk about the acquisition process. To put things in perspective, we were scheduled to hold our Industry Day coincident with the Space Symposium in Colorado on April 2nd. The pandemic hit, which of course no one could anticipate. We still held our virtual industry on April 2nd. 1 month and 1 week later, we released the first RFP, which was for the transport layer. That was on our original schedule. We went through the source selection process, held a best and final, and then down selected for award and time to announce on September 1st. We pushed hard to do this, and we are really proud of the solicitation and that we were able to keep to our timeline. The tracking layer awards followed shortly after. They pushed equally hard, and SDA was able to award 2 additional contracts on October 2nd. For those of you who have been involved in government procurement, that is fast. Don Brown of Telesat was quoted in Space News as saying, "They did it in months. It surprised the heck out of us." I love that. I love that we're getting that sort of reaction. Efficient procurement is the first step in getting new technology to the warfighter rapidly, and we are doing everything we can to achieve that objective. Let's talk about those recent awards. Lockheed Martin and York Space Systems were selected to design and build a total of 20 Tranche 0 transport layer satellites. Those will be ready to launch at the end of FY22. For the T0 tracking layer, L3 Harris and SpaceX were selected to build a total of 8 spacecraft, with wide field of view overhead persistent infrared sensors capable of tracking advanced missile threats and passing those tracks to warfighters through the transport layer. These systems will also be delivered for launch by the end of FY22. Now that we have a good background on SDA, we can start to talk about the optical intersatellite links. Tranche 0's transport layer will be comprised of 2 planes of satellites with 2 groups per plane. Group A will consist of 7 spacecraft per plane, and each spacecraft will have 4 OISLs. Group B will consist of 3 spacecraft per plane, and each spacecraft will have 2 OISLs and a Link 16 system. In addition to the transport layer, tracking will field 4 spacecraft per plane. These will include 2 OISLs per spacecraft, along with the tracking mission sensors. The key demonstrations in T0 will be in-plane, cross-plane, and space-to-ground links. Through communication between the 4 T0 vendors, we will demonstrate the vendor-to-vendor interoperability that is so important to our mission. The notional T0 network is shown in the image to the right, and you can see the 2 planes that are providing connectivity between Hawaii and Maryland through a cross-plane optical interlink hop, along with an uplink and a downlink. This will provide high bandwidth communications with a lower latency than can be achieved with current long-haul communication solutions. I already mentioned the importance of the optical intersatellite vendor interoperability. The Tranche 0 RFPs included the first draft of the OISL standard, and we're working to refine that standard as part of the Tranche 0 effort. The draft standard has been approved for public release, and you can find it on the SDA website. The OISL standard provides an interface specification that will enable interoperability across the vendor base. This is a crucial enabler of the Tranche 0 missions, and we are working to rapidly converge on a baseline for the specifications. We'll be working to improve this standard both to support future SDA tranches and to enable that crucial government and industry connectivity to the SDA mesh network. I get asked about the standard regularly. People say to me, "Mike, my free space optical system does X or Y, which is different than everyone else's OISL. How do I make sure the standard supports my technology? Or, conversely, how do I make my technology support the standard?" Part of the tight government-industry partnership I mentioned before is enabled by the OISL community of interest. The COE consists not only of government representatives, but also of industry experts who can help enable interoperability of non-SDA OISLs with the SDA mesh network. How do you get involved? Contact me. My email address is on the slide, and SDA is interested in your contributions to the OISL standard. I'm going to end with SDA's motto, Semper Citius, Latin for always faster. When we say Semper Citius, we mean that we are moving at or ahead of the speed of the threat because we know that the joint warfighter is counting on us. Thanks for listening, and I look forward to your questions.